Test. All right, who's ready? Oh, we got a little green screen. Oh no. Can I fix that quickly? Sure. Hey, that's good. All right, we did fix it quickly. All right, let's go for it. Lecture 2. Did I say summer moves fast? We're gonna finish up Intro to Java today. We're gonna do this loops and conditionals and data structures. And then Tuesday we'll get into unit testing, and then the big lecture 4 I keep foreshadowing when we talk about classes and objects. So let's dive right in. No reason to wait. As always, if you have questions, feel free to hit them in chat. I'll be watching chat the whole time. It's when I look over here, that's chat. And what's my keyboard shortcut for full screen? We'll get this really down today. Control-Shift-F. Oh, but I don't want full screen. I want presentation mode. Control-Shift-P. All right, so we very briefly started this. We got just past the one slide till I said it's a memory diagram last time. So let's kind of recap. We'll take it from the top and go right into it. Go right into that memory diagram. So this is our first conditionals example. We have an if statement with else if and else. Not too much difference. From Python, we mentioned the differences last time. The syntactical differences are braces instead of indentation, else if instead of elif, because Python likes to randomly just delete 3 characters, but only in that instance. I don't know, usually Python's so verbose and explicit about things, but not just in one case they're not. It's weird. And then we're going to call this method 3 times. We're going to expect A, then C, then F. All right, so that's a quick recap of the example that we talked about last time. Now let's go into that memory diagram. So let's grab the code. I'm going to go over to IntelliJ. I'm going to complain about Windows, and then we're going to do this memory diagram. Frickin' Windows says, I just remembered because IntelliJ was closed. Windows said, hey, do you want to restart? Your choices are now or in an hour. And I would like to choose don't restart. Like, why the hell are you restarting? And that wasn't an option. So I had to restart, and then Windows would not boot again. It just kept bringing me to my BIOS, and it kept bringing me to my BIOS and wouldn't start. And I was panicking. I thought I bricked the machine, and eventually I tried it 5 times, and apparently number 5 was the magical one, and it finally actually booted. So now I'm afraid to ever restart this computer, but here we are. I thought I was going to have to do this stream on my laptop. It was close to a disaster. We might have been in a Zoom meeting, and I don't even want to think about the backup plans. There are backup plans, but they're not great. Okay, so let's do this memory diagram. And the big thing that we're going to start seeing in today's memory diagrams are code blocks. This is something that apparently doesn't come up in 115 because Python handles code blocks differently, but in 116 we do have to care about our code blocks. Morning, Dave. And we'll do No, I already said it. We'll do the code blocks. So let's start this memory diagram. This is our second memory diagram, so I'm still going to explain the main method a little bit. Every Java program starts with the main method call. That is a method call. Every method call has a stack frame, so every single Java program ever is going to start with a main method stack frame for all the variables in the main method. And then our first line here, we have, again, something different. This is something you've seen in 115 extensively, but if you haven't taken 115, it's your first time seeing it, is a method call that's where the result is being assigned to a variable that is being declared on the same line. So we have string result equals letter. We're declaring the variable string of the variable result of type string and assigning it the value that this method call evaluates to. So when we do that, in our memory diagrams, we actually put our variable on the stack first. Technically, it's not what the computer is going to do. It's going to resolve the right-hand side and then worry about the left-hand side. But we're going to put our variable on the stack first and then create the stack frame for our method call. Every method call has a corresponding stack frame. We're going to create our stack frame for this method call of letter. That takes actually, let me do the other thing first, since that's what I was starting. And the reason we put this variable on the stack, even though it's not going to have a value yet, it needs this stack frame to resolve, this method call to resolve, before it can get its value. We're still going to put it on the stack so we can have our return arrow. So our method is returning into a variable. We're going to need that variable to exist so we can put our return arrow there. So we do create our variable on the stack first and then put the return arrow for that stack frame into that variable. Otherwise, we'd have no place to put our return arrow. So that's the only reason we do it in that order, is putting our empty variables there. Okay, our parameter is called score. It's getting the argument 98. And then we're ready to run the method. And this method is going to return a string, so all my return statements better be strings. And I have multiple pass through this method, so no matter what set of conditions are true, every single situation better result in returning a string, or else Java's not going to run our program. So luckily we have that case, not luckily, but we have that case here. If the if is true, we return a string. If we get to this else if, we return a string. This else if, we return a string. This else if, we return a string. And we have an else that returns a string. So we're always returning a string. If I don't have this else, if this isn't here, Java's not going to run this code because it's going to say, well, what if all of your conditions are false? You don't have an else, so in that situation, you're not returning a string. So we have a path through the method that doesn't result in returning a value of the return type. Java's not going to be happy about that, and it's going to say expected string got void, I think is what the error message says. When you see that, check your conditionals to make sure you're always returning the correct return type. Okay, let's go through this method. Int tens equals score over 10. So we have a new variable tens, and it's going to get score, which is 98. 98 divided by 10. These are both integers, so we're going to get integer division, and tens is 9. So we don't get the 9.8. Remember, this is integer division. We don't get the 9.8. We get just 9. The 0.8 is destroyed. It's just gone. And the reason, I'll get to finish this conversation on Tuesday, but the reason we're talking about, I don't want to word that. The reason we're talking about integer division is because it's important. Like, it's something you got to know. But the way I have some of these examples set up in lecture is specifically to show you a good strategy to do that sum of digits method on task 1. If you're taking advantage of both integer division and modulo arithmetic, if you use divide by 10 and modulo 10, there's a solution in there, a way to approach that problem that's pretty clean. So that's where I'm making sure you know how to use this modulo arithmetic, and an example of where this integer division and modulo arithmetic, but where this integer division can be helpful to you, where you actually don't want the decimal portion, you want it to be truncated. That's a good example of where we want that. So we're taking advantage of that here as well. We only want the tens digit, so we're going to integer divide by 10. That's going to give us just the tens digit. And then if tens greater than equal to 9, tens is 9, so 9 greater than or equal to 9 is true. We're going to return A. Just shuts down the whole method right there. So we cross out the stack frame, and this gets the value A. Then we're back in the main stack frame. We're going to print A. Or rather, we're going to print the value of result. The value of result is currently A. We're going to print A to the screen, and then run it back again. Result equals letter of 75. We're going to put another stack frame for our new method call. And we don't have any way... I always get this question, so I got to address this one. Is we don't have a way that we're going to distinguish between different method calls. We have 2 calls. We're going to end up with 3 calls to the letter method in this program. All 3 of those code stack frames are all going to just be called letter. We're not going to specify like what the parameters are or what the arguments are or anything. We're just going to call them all letter. And in the context of the final trace, like we'll be able to figure out what's going on. Mostly by looking at the first line, that's going to be the parameter and the argument. So I know this was the call of letter with score being 98. And then this one, score, the parameter is going to be assigned 75, the argument. So we'll be able to look at the values in the stack frame to tell if it is, if everything happened the way it was supposed to. So we don't need any extra information in the name of the code block, just the method name. Okay, 75, tens equals 75 divided by 10. So tens is going to be 7. Tens greater than equal to 9 is false, so 7 greater than equal to 9, false. So we go to the else if. 7 greater than equal to 8 is false, so we go to the next else if. 7 greater than equal to 7 is true, so this is the code block that we're going to execute. So here's where I really want to talk about code blocks, because you can kind of gloss over code blocks in Python a decent amount. We need to focus on them in Java, though. We need to understand our code blocks. So in Java, whenever you have a pair of braces like this is defining a code block. So this right here is a code block or a block of code, but I'll usually say code block. This is a code block. It's a way of organizing code, I guess, of sectioning off code, and it has special properties. Now we already have some code blocks here. We have the code block for a method. Code block for a method creates a stack frame, so we treat those quite a bit differently, and those are the same way that they behaved in Python anyway. So those will create stack frames, and we have the code blocks for classes themselves, which is our container for all of our stuff, all of our code. So that one's treated a little bit differently too. But now that we're getting into conditionals and loops today, we have to treat these code blocks a little different. These are code blocks that are inside methods. Those are our conditionals and loops, are the 2 cases we're going to see that. In these code blocks, any variable that's declared inside your code block must be created inside a code block in your memory diagram. So we're going to click the code block button here, create a code block. We're going to get this dashed box. We have the difference between dashed boxes and solid boxes. Stack frames are solid boxes because stack frames are isolated environments. You cannot escape a stack frame. The only way to get out of a stack frame is to return out of that method, end that method call, and remove that stack frame from memory. A code block is a dashed box because we can cross the line of the dashed box. There are certain rules of of what we can do here. And we can access any of these variables that are outside of the code block as long as you're still in the same stack frame. So we're still in the letter method inside of this code block, so we can still access score and tens with the value 75 and 7. Not these two. These two aren't even in memory anymore. That's crossed out. That means those do not exist. But this variable result, this has to be declared inside the code block because it's declared inside the code block. So since this variable was declared inside this block of code, in our memory diagram, it has to be placed inside that code block in the stack. The reason for this, which isn't actually going to come up in this specific example, I'll be able to highlight it in later examples today. The reason we do this is once a code block ends in Java, and in most languages, Python's a little weird that it doesn't. When a code block ends, any variables that have been declared inside that code block are destroyed. So once we hit the closing brace of this code block, we cross out the code block, and then this variable result does not exist anymore. It's not in memory, just like when a stack frame ends. All the variables inside of that code block are gone. They are just completely destroyed. So we cross it out to indicate that. In this case, we actually hit a return statement. So the stack frame and the code block are both destroyed at the same time. So it's so we don't get to see the actual effect of that, but these do both get crossed out. And we're returning result, which is C. And remember, we always cross out variables. We never just change a variable name. We never erase any history. So we don't want to erase the fact that result used to have the value A. So we cross it out using this plus button, cross it out and type in the new value. And then we're back in the main method. We're going to print result. Result is the value C right now. And then run it back. And this last call is going to look just mostly like the first call. We're not going to have a code block, but let's get this one in here. So score, we have a parameter named score. Assign the value 30. So we skip the code block if it returns a value right away. No, I didn't skip the code block. In this one, this call that's about to happen, let me get tens on the stack and then I'll get that one in there. So tens is 30 divided by 10 is going to be 3. 3 greater than 9 false, 3 greater than equal 8 false, 3 greater than equal to 7 false, 3 greater than equal 6 false, so we hit the else. So we are in a code block right here. So what we can do, and it's technically correct, to create our code block with no variables in it. So we can do this. Because we did hit a code block, we can put the code block in our memory diagram and just have an empty code block. That's perfectly fine, and if you want to do that in your traces, that's perfectly fine. You submit your quizzes with empty code blocks, perfectly fine. But when a code block doesn't have any variables in it, I'm going to opt to just not put that code block there at all. So technically we did enter a code block. We can trace it. But if there are no variables declared inside of that code block, then the code block has no effect. So there's no real point to tracing it. And we give you the option, and I'll take that option in lecture, to just not put the code block on your trace at all, mostly because it reduces the clutter of your trace. If you have all these empty code blocks every time you have a conditional that doesn't declare any variables, it's going to clutter up your trace. It's just going to look a lot messier. And look, it already looks kind of messy. And this is a pretty simple memory trace. These things get big. They get complicated. Anything we can do to make them a little cleaner, we're going to take advantage of that. So I'm going to opt to not put my code block in the stack here and just return F. And it's my biggest thing, I always forget the return arrows. So this just returns F, cross it out, cross out this value, F, and then back in the main stack frame. So if you're in the middle of a trace and you kind of lose where you are, where you are in the code, or at least what method you're in, is start from the bottom and go up. The first stack frame you hit that's not crossed out, that's the main method right now, that's where you're currently executing. That's the top of the stack. So we go back to the main method. You do have to remember what line you were on though. And we're printing result here, which has the value f, and print f to the screen. So we get ACF like we expected, and that's how we go through the program line by line, exactly what's happening. We hit the end of the main method, cross it out. Yeah, and if you have your if you have your empty code blocks, or if you just don't put them there, first of all, you have the option. But even if I did say you have to put your empty code blocks, or never put your empty code blocks, you're right, it wouldn't be anything that would affect your grade. That would be considered an extremely minor mistake. There would be, in our actual real world, it's not a mistake at all. But if I did require one of the two, I wouldn't care. Because it's not going to have anything. Again, going back to what we said last time, if you either put or don't put an empty code block, that has nothing to do with classes, inheritance, linked lists, or trees, the 4 topics that we're assessing you on with the quizzes, with the midterm and the final and all these traces. That has nothing to do with any of those 4, and that would never alter your trace in such a way that we wouldn't be able to assess those 4 topics. Because whether you put your empty code block or not, it doesn't have any effect on your trace at all. We're still going to have all of the information that we need to be able to tell if you completed the learning objectives or not. So it's something that would never actually matter. But I did want to highlight that they are technically still there. So the question of when do you need your code blocks? Well, whenever you hit a code block, if you see an open brace while you're inside a method, it is a code block. So if you just want to do that and just always put your code blocks on the stack, that's perfectly fine if that helps you remember to always do your code blocks. But when it's absolutely required is when you hit an open brace, and then before you hit the close brace, the end of that code block, there's a variable that's declared. And remember, a variable declared, you can always tell when a variable is being declared in Java because we're specifying the type. We're specifying the type, that means we're declaring a new variable named result with type string, as opposed to a reassignment where we're not specifying the type. This means we're reusing an existing variable. So for example, if we reassign tens inside this code block, tens is still outside the code block because it was declared outside of the code block. But here, and if we reassign it inside of a code block, that variable doesn't then move into the code block. So if I'm declaring a variable inside a code block, that's when it's required. That's when you have to have it. Okay, any other questions on this trace? We're making good time. We're going to definitely get all the way caught up today. And after we get through all the content, I want to do some IntelliJ demo, how to get IntelliJ all set up. Okay, if there are questions, hit me up in chat. I can always jump back to this tab. Where are we? Ocular. Control-Shift-P. Okay, we're getting our shortcuts down. And then, as always, I'm going to leave my slides for the traces. It's obviously a very different format than what you're going to see in the tracing tool, but it's the same content, it's the same exact information, and you have my bullet points here. So if you do want to review the memory diagrams, this can still be a good tool for reviewing them, or watch the video, of course. But if you don't want to watch the video, if you reading slides, if that's your preferred study method, I still want to leave these in here so you have that option. Okay, let's talk about loops. So the old while loop, let's talk about it. Which I think they cover while loops in 115 now, but if you're not coming from 115, I still want to talk about it. A while loop, plus it takes like 10 seconds to talk about. A while loop is very much like a conditional in syntax, at least. It's like an if statement. It's like saying if this, then do this. The only difference is after the code block ends, after you get to the end of the block, you go back to the conditional and check it again. And if it's still true, you run the block again, then you check the condition. If it's still true, you run the block again. If it's still true, you run the block again. You just keep going until the condition is false, or rather, while the condition is true, keep doing this. That's why it's called a while loop. You're just executing this code block while this condition is true. This is a Boolean expression, just like a conditional. That's all I got to say about that. We will do a memory diagram on both of these loops that we're going to look at. So when we get to the memory diagram, we'll go through exactly what this code does. It does, mostly what you'd expect it to do, but there are a few nuances that might not be immediately obvious, and we'll talk about them. And notice that your loops might never execute. Just something helpful to always keep in mind. If you're writing code that relies on your loop executing at least one time to be able to operate, sometimes your loops don't execute at all. So when we get to this while loop, the condition is false already. -5 is not greater than 1. So we go right to the end of the block and continue with our code. So just always keep that in mind. If you have usually empty data structures is where this comes up. What to do when we have an empty data structure, we can't rely on our loop code setting up any variables or initializing anything. Like if you're finding the min value of an array list of some integers, and you initialize your minimum to some arbitrary value, something arbitrarily high, and you're relying on your loop to override that value with a value from the list, well, that's not going to work for you if your list is empty. You're going to get whatever your default value was as your return value. So things like that, we just always got to be aware of. Then the for loop. This one's new. I'll spend a bit more time on this one because Python doesn't have these types of loops. Python has only what Java calls enhanced for loops, or what I think most people call for each loops, where you're always iterating over a data structure. Java has those too, and we're going to see them later today. But Java also has what is like the original for loop. This used to be the only type of for loop. Now that for each loops are very prevalent, usually we're just pulling out our for each loops instead. But this type of for loop is going to be helpful. You're going to need to use this in Java for certain applications, certain situations where you can't just iterate over the data structure. We're going to need to use this a couple times throughout the semester. So let's talk about what it is. First of all, the for loop has 3 statements, and this middle one, this one we already know about. This behaves exactly the way it does in a while loop, which is why I wanted to talk about while loops primarily. So for x less than 5, as long as x is less than 5, we're going to keep looping around. We're going to loop, check, loop, check. As long as this condition is true, we're still going around this loop. So that much is the same as a while loop. But we have these 2 extra statements. These 2 extra statements are the initialization statement and the increment statement. So what this code is going to do is when we first get to this loop, we're going to declare a variable named x of type int and assign it the value 0, so a regular variable initialization and declaration and assignment. And then we're going to check the condition, and if it's true, it will be true in this case because it's 0 less than 5. We're going to execute the loop, the body of the loop, and then each time we get to the end of the loop, we're not just going to check the condition again, we're going to run the increment statement. So we're going to increment x by 1 in this case, then x will be 1. We're going to then check the condition, and if the condition is true, we run the body of the loop again. We go to the increment statement, execute this, then go to the condition again, and keep doing that until the condition is false. And a few syntactical things, or I guess one syntactical thing, this x plus plus, this is the same as saying x equals x plus 1. or x plus equals 1. I think you see in 115, if you see x plus equals 1, that's the same thing, x equals x plus 1. Java and a lot of other languages take this one step further and give you the option to do x plus plus, which just increments x by 1, which is exactly what we want for this loop. So in general, we have an initialization statement that's executed exactly once when we first get to the conditional, or when we first get to the for loop. We have a Boolean expression that's checked each time we're checking should we run the body of the loop. We have the increment statement, which runs after you run the loop body, each time you run the loop body. And then the loop body itself, which is, the code that you actually want to control using this loop. And we're ready for memory diagrams. Let's go right back to the code. So I want to grab my loops. These are the two loops that we just saw in the slides. No one had questions on this one? I assume not, or else somebody would have been in chat. So let's clear that. Get our loops here. Full screen. Hide toolbar. Let's do some loops. So it's Java. We're going to start with a main stack frame. That's a given. You can do that before even looking at the code. You can create your main stack frame. It's how every single Java program is always going to start, is with a main stack frame. All right, first thing we do is create a variable named val with the value 10.0. Oh, that is a little different than in my slides. And I'm going to change it to the way I have it in my slides, just to emphasize this point, is I have a variable of type double being assigned a value of type int. Because I don't have any decimal portion, Java is going to treat this 10 as an int literal. So this is going to be a value of type int. Just like when we didn't put any decimals, we ended up with integer division in lecture 1 when we had 6 divided by 4. If we had 6.0 divided by 4, we wouldn't have got an integer division because we have a double divided by an int. Okay, and so we have an int. Usually this isn't allowed. The type of the value must match the type of the variable. Pretty much always in Java. There are a few exceptions. This is one of them. Is if you are assigning an int to a variable of type double, Java will auto-convert this for us. We can always convert an int into a double without loss of precision because every single possible integer value can neatly fit inside of a double. There's no concerns there. So Java will convert this 10 into a double. That's why when I put it on the stack, I put 10.0, because by the time it's stored in val, it will be converted into a double. And it's going to be important because we do have a division here, so we need to know if this is integer division or not. So val will store a double, because it is of type double, it has to store a double. It doesn't have any other option, but we can assign an int and Java will take care of that conversion for us. If we were to go the other way around and say int val equals 10.0, that's not allowed because with a double, you can't fit every possible double into an int because you're going to lose the decimal portion. So you're going to get an error that says, warning, loss of precision. You don't want to do that because you're going to truncate the decimal portion. And also you can have larger values in doubles than you can in ints. So you're going to lose that precision as well. If you have a very large double, you're not going to be able to fit that in an int, even if it's a whole number. But this is allowed. This is the one thing we can do. Integers being turned into doubles. You can do that all day. Okay, then val greater than 1. And here again, we can see the conversion. This 1 is going to be converted into a double before the greater than operator is evaluated. So val 10.0 greater than 1, that's true. So we're going to execute the body of the loop. Now I can look ahead a little bit. look at the body of this loop, and I see that no variables are declared inside this loop. We do have val that's reassigned, but val was declared outside of the loop. It's already on the stack before we even get to the loop. So we could create our empty code block. That's perfectly fine. But we don't have to here because we're not going to have any variables declared inside of this code block. This code block will just be empty. It'll just say no variables the entire time. So there's no reason to trace it. You can if you want, if it helps you remember what to do. You know what, I'll even leave it on the stack for this example. But there's not going to be anything in it. It's just going to have no variables. Actually, I'll leave it in the stack until the end of this loop, and then I'll say, hey, look, we created it, but it has no variables, so let's just delete the thing. So the condition is true, so we're going to execute the body of this loop. We're going to print out val. Val is 10, 10.0. And then val divided by equals 2. This, again, some new syntax. In 116, I'm going to throw new syntax at you. This is part of the expectations of the course. I expect you to want to learn about computer science. That means you're probably ready for more like tips and tricks style stuff instead of just the absolute bare minimum to be able to get through the course. Like, I assume you want to be here and you're like, oh, divide by equals. That's something convenient I can use in my code. That's neat. So I will sprinkle in more of those types of things than I would if it were a 115, for example. So val divided by equals 2, this is just like plus equals. You can do plus equals like you presumably did last semester. If not, I can show you real quick. Plus equals is the same thing. This means val equals val plus 2. So I would increment val by 2. I'm doing divide equals by 2. Val is a double and 2 is an int. Since not both of them, they're not both ints, so I'm not going to get integer division. Val is a double, so I can't have integer division when a double is involved. So I'm not going to get integer division, so I am going to retain the decimal portion, and then I'm going to reassign the quotient back to val. So I have val equals val divided by 2. So val is going to be updated to the value 5.0. We've reached the end of the code block, so we're going to check the condition again since we're in a while loop. 5.0 greater than 1 is true, so we're going to run it again. We're going to go through this again. We're going to print out 5.0. We're going to divide val by 2. Is x plus equals a always the same as x equals x plus a, or is it weird like in Python? To my knowledge, it's exactly the same. I think it's just different syntax. But if there's some really obscure difference between the two that I'm not aware of, I want to hedge my bets a little bit. I'll say I'm 99% sure it's the same. But, of course, I don't know what the weirdness is in Python either, so I'll table that one. I'll say that it's not going to have any weirdness that will affect us in 116. If there is some weirdness that I'm not aware of. That got me thinking, what is the weirdness in Python? Maybe type conversions? Maybe it has some weirdness with types? No, I don't know. Yeah, if you want to let me know what the weirdness is, maybe I'll learn something today. I don't know what the weirdness is in Python. So we're going to divide, where are we at? 5.0 and then divide. So we're going to divide by 2 again. So 5.0 divided by 2, 2.5. Get to the end, check our condition. 2.5 greater than 1. Run it back. 2.5. Divide val by 2. It's going to get a little repetitive, but I got to get to the end of this one because there's a point I want to make at the end here. Go back to the condition. 1.25 greater than 1 is true, so we're going to go through the loop again. This is why we like loops, though, because they can be repetitive, so we don't have to write all this code each time. The loop just takes care of a lot of repetition for us without us having to think. Then val divided by 2 should be 0625. We at the end of the block, so we check the condition again. Val greater than 1, 0625 greater than 1 is false. So we go to the end of the code block and continue on with our program. At this point, we would cross out the code block. Now I have no variables here, so this had literally no effect on our code, on our execution. Nothing went in memory, so it has nothing to do with our memory trace. Nothing happened in memory during that code block. We updated a value that was outside of the code block, but we didn't do anything inside the code block. Namely, we didn't declare any variables inside the code block. So there was no point in tracing this. So usually I'll just skip tracing this. I'll leave this one here, this one time. Hopefully that doesn't cause confusion. I hope it doesn't. But I will leave this one right here for this one example. So the end result here is we get 10, 5, 2.5, 1.25 printed to the screen. But the end value of val was 0625. So we did get a value of val that was never printed to the screen. So val got to a value where we never executed the body of the loop while val had that value. So there's little nuanced things like this that need to be teased out when you're doing your trace. And the easiest way to catch every single little thing like this is to not overthink your traces. I said this last time. I'm saying it today. It's not going to be the last time I'll say it. I'll say it again throughout the semester. But don't overthink your traces. Just go through the code and do what the code tells you to do. Just line by line, blindly, just like the computer does. Check the condition, and just like I did. There's a reason I spelled out every single step there. That's the way you should approach these traces. You declare a variable val, assign it a value, get to a while loop, check the condition. If it's true, run the loop, check the condition again, run the loop. Just go exactly the way the computer is going to go. There's too many students end up making mistakes on traces because they overthink it. And what I mean by that is they'll look at this loop and they'll say, oh, val's gonna divide. They'll read the whole code, interpret it, find the patterns, do our human type of stuff, not computer type of stuff, and say, okay, this is going to keep dividing val by 2 until val is less than or equal to 1 and print it to the screen each time. So it's going to go, starts at 10, so it's going to do 10, and they'll go right to the I.O. 10, 5, 2.5, 1.25, and get all of their I.O. without actually tracing the code. They're just predicting what the code's going to do. And then they'll go to their stack and put val 10, 5, 2.5, 1.25, and then go on with the program and execute the rest of the program. When they're doing that, what they miss is the 0625. And if I don't see that 0625, I know you didn't actually trace the code, at least didn't trace it properly. But if you just trace through the code, just go through every single step. I mean, you have plenty of time on your quizzes when you're doing these. If you go through every single step, you're not going to have any opportunity to make mistakes like that. In Python, it's weird with lists. Oh, yeah, I didn't. Yeah, Java doesn't let us do that with lists. So, yeah, I could see that being weird with lists. Yeah, I can see that. I would not. Personally, I also wouldn't use that operation with lists. That just seems like it's asking for trouble. If you have 2 lists and you want to concatenate, yeah, that's asking for trouble. So we're going on with the program. Once the condition is false, that code block is over, that loop is over, and we go on with our program here. Now the for loop, this one, and I purposely didn't mention this in the slides because I want to talk about it now. But so we're talking about code blocks, and I'm highlighting the code blocks and everything. There's kind of one exception to what's in a code block, and that's the initialization statement. Initialization statements in for loops do execute as part of that code block. So when we get to the for loop, we immediately need a code block for that loop, and x with the value 0 is declared inside that code block. So we have x equals 0 inside the code block for the for loop, meaning that when this for loop ends, x is going to be destroyed. So with that, let's go through our loop. We ran the initialization statement exactly once. We're done with that one. And then check the condition. 0 less than 5 is true. We're going to execute the body of the loop. So we're going to print x, which is 0, to the screen. We get to the end of the loop. So we go to the increment statement, which will increment x in this case. And then check the condition again. 1 less than 5. That's true. So we're going to print 1 to the screen. Increment x. 2 is less than 5. We're going to print x to the screen. 2. Get to the end of the loop. Run the increment statement again. 3 less than 5 is true. So we're going to run the body of the loop again. Get to the end of the body. Hit the increment statement. Increment x to 4. 4 less than 5 is true. We're going to print x to the screen. 4. Get to the end of the loop. So we're going to run the increment statement again. Increment x to 5. And then x less than 5. 5 less than 5. That's false. So we go to the end of the loop. That's the end of the loop. So the end of the code block. So we're going to cross out the code block, which means we're removing x from memory at this point, and then move on with the rest of the program. So this is the first time where it really kind of matters that x is destroyed. That x is no longer in the loop or in memory. That code block was destroyed along with every variable that was declared inside of that code block. So x is no longer in memory. It's no longer accessible. It's just completely gone. It's destroyed. So if you're trying to access x outside of this loop, you might wonder, like, what happened to my variable x? I declared a variable x. I declared it right here. It definitely exists. Well, no, it doesn't. Once you hit this closing brace, x literally does not exist anymore. It's actually erased from memory. It is completely gone from memory. So you cannot access x after that code block ends. And then in this case, the program just ends is the next thing that happens. So we cross out our main stack frame and the program's over. So notice with the second loop also, x got a value of 5, but 5 was never printed to the screen. We never executed the body of this loop when x equaled 5. But x did actually get to the value of 5. So again, the way to take care of that, like I didn't do anything special when I was tracing the code. All I did was trace the code line by line and just blindly go through exactly like a computer, which does not think. It just goes line by line following a set of rules. That's the same thing I recommend you do on the traces. Just blindly go through following your set of rules. Okay, this is a conditional. I check that resolved to true, so I'm executing this code here. Then I'm going to go to the increment statement and check the condition again. I just went through that without thinking at all. I kind of turn my brain off sometimes when I'm doing these traces. And I ended up with the right values here. I ended up with the right x, the right things printed to the screen, but doing less work than some students want to do. A lot of students have even failed quizzes because they think too much. It's always weird advice. I always feel weird saying this, but they'll think too much when they take these quizzes. You don't want to think too much. You want to become the computer, become a clump of silicon and copper, and just blindly go through the code and do the code each line. Just remember what the rules are. Each line, do what it tells you to do, and don't overthink it. Students will get to this one and they'll think, oh, that's going to print like 0 to 5, and they'll print 0 to 5 to the screen, and they'll miss the nuanced points like, no, this is strictly less than, so it's 0 through 4, but x is 0 through 5. They're going to miss that. you're never going to miss that, and you're never going to have to memorize, like, wait, okay, Jesse said that the variable will be the next value but not printed to this. You don't have to remember any of that. Just go through the code. Remember how a for loop works, and just go through the code step by step. Okay. And I want to emphasize a little bit of that in IntelliJ. So first we can run this. Do I do an IntelliJ tutorial right now, maybe? You know, since I want to show some stuff, let's do an IntelliJ tutorial right now. Yeah, let's do it. And talk a little bit of how this works. So first, IntelliJ, you can find it on the course website. One of the first links here, IntelliJ. And I always recommend the Ultimate Edition because it has a bunch of extra features that you might find useful at some point in your careers. I think I'm going to stop recommending it, honestly. The Community Edition, if you scroll down a little bit, the Community Edition is free for everybody, and you can just download it right away. The Ultimate Edition you can still get for free with an academic license, which you can get for free because you have a .edu email address. So you can get Ultimate for free. There's a few extra steps involved, and I don't know how many students actually take advantage of the Ultimate features. The Community Edition does everything you'll ever need for 116, and in fact, what I'm going to use this semester is the Community Edition, just to prove that point, that the Community Edition will do everything you need for 116. There's no reason to use the Ultimate for 116 specifically, but if you already have Ultimate set up, then as you continue to work on like side projects and other courses and stuff, you'll have all the features of Ultimate already there. But the Community Edition will do everything you need it to do. So once you have IntelliJ installed, you're going to I have to break this just so I can make this point. I didn't show cloning in the other lecture, did I? Yeah, let me start with cloning. Let's do all our IntelliJ stuff right now. Let's get it all out of the way. So when you go to the course website, go to the lecture examples repo. You're gonna get this. And last time I said, oh yeah, click through these things. You can find all this stuff. That's not the way we actually want to interact with this code, though. I want to go to code and copy this link right here. That's going to give me a reference to that GitHub repo. And then I want to, in IntelliJ, yes, I want to exit. Oh, actually, no, I didn't want to exit. I just wanted to close that project. Close project. Oh no, oh no, oh no. Where did that go? Oh, I just grabbed the wrong spot. It was on my other monitor, and then I started messing it up OBS. Yeah, okay, that's fine. All right, so when you first start IntelliJ, like, why did everything minimize? Like, what the hell, Windows? Really pissing me off. When you first install IntelliJ, you get this. You won't see class example code here. And if you do clone repository and paste that URL that we grabbed from GitHub, paste that URL. I have to do one extra step here. I have to put like a 2 here. You won't have to do that, but actually I'll show you why. And then I'll click clone. It's going to get mad at me because I already have a directory with exactly this name because I've already cloned this repo once. So if you ever do get this, put something like 2 here, just something so that's a different directory name, and then clone. And what that's going to do is download all of that code for that repo, and of course it puts on my second monitor. It's going to download all of the code for that repo and put it into your IntelliJ, download it to your computer, and do a bit of setup. It's got some progress bars here. It's going to do a bit of setup to hopefully get everything the way that we want it for the course, except one thing that I want to show. It's going to work here because I already have it set up, but when you have it set up, you're not going to have an SDK downloaded. So you're going to get this error on all of your files, and then you're going to click Setup SDK. You won't have these options because you won't have any downloaded yet. So click Download JDK, and then use the defaults, whatever default it gives you. Right now it's Java 24 is the most recent version. I always make sure everything in the course works for the most recent version of Java, so you can just download whatever it tells you to download here. And once you get that, once you click download, it'll usually take longer, but I already had it downloaded, like it didn't have to do as much. But it'll say indexing down here, and it'll take a minute, and then all the error messages go away, and we can run the code. To run code, we have this go button here, this go button here, or what I always prefer is right-clicking the file and using this go button here. I prefer that for reasons that we don't have to get into right now, but I've clicked the wrong button over here before. They all do the same thing in this example, it's just hello world, but sometimes these will do different things. And we get hello Java printed to the screen. So we officially ran that Java program. And that's, I'll leave it at that for lecture. There's also the Piazza post. There's a Piazza post about IntelliJ setup. You can go through that. You can also come to office hours. We'll be happy to help you in office hours to get things set up as well. All right, that's everything I need to say about IntelliJ. If there are still questions about IntelliJ, let me know. I think I hit all the key points there. And then when you start your homework too, when you start task 1, there will be a repo to clone, and that'll be the same repo throughout all 8 tasks. It'll be one project that you're working on the whole semester. So you have to do that one more time to get the homework code, all the programming task code, and then you'll be done with IntelliJ setup. We shouldn't have any IntelliJ setup after this first week. That's the goal. All right, so a few things I'm going to add here. I'm going to print out val after this while loop ends, and I'm going to, let's just run that actually. And I can just verify that val did get the value 0.625, even though it wasn't printed to the screen in the loop. But just to confirm that our memory diagram did what it was supposed to, not what it was supposed to do, but our memory diagram was accurate. So just kind of a proof of concept here. And then I'm going to print out x. I want to do the same thing here and print x to the screen. And I'm not going to be able to do that. That's not allowed. So we're going to get an error here because x, as soon as we hit this closing brace, x was destroyed. It was destroyed along with that code block. You completely erased from memory, and Java's going to say can't find symbol. And if you don't understand code blocks, this can really drive you insane. The can't find symbol, because you're going to look, it's right here. I declared it right here. And we can even make it somewhat more obvious too. I can declare y inside of that code block, and okay, int y equals 7, print y. Run. Oh, there's a go button up here too. Be careful with that one. I'll explain that in a sec. I just gotta finish this point. Can't find symbol y. Can't find y. Cannot resolve symbol y. And you're gonna be like, why? It's right friggin' here. I just declared it 3 lines up. How the hell, Java, can you not find my variable y? And you're gonna start pulling out your hair and going through this really crazy debug cycle trying to figure out why it possibly can't find the value y when it's right friggin' there. And then once you understand code blocks, all that frustration goes away and you say, oh, that's because y was declared and x were both declared. Let's get them both on here. Especially the x, because it's like I just printed it here and then 2 lines later I'm trying to print it again and you're going to tell me you can't? You just did it right here. What the hell, man? And once you understand code blocks, you know that the initialization statement is part of the for loop code block, and this y was declared inside of the code block. So once this code block ends, both those variables are destroyed. They're gone. They're erased from memory. Therefore, we cannot access them again. These variables actually do not exist after that code block ends. Those variables are gone. They are destroyed. They're removed from memory. They're deleted. Completely gone. So no, we can't access them, and they actually don't exist. Java is correct that these don't exist. If for some reason we do, I shouldn't say for some reason, this is a situation that we often want. If we do want those variables after the block ends, we need to declare them before the block starts. And by the way, our initialization statement, I don't often use this, and because I'll usually use something else, a while loop maybe. But the initialization statement can be blank. We can just leave it completely blank and start our expression with a semicolon. So this says that I'm done with my initialization statement and just don't have one. And actually we can have a blank increment also. But the warning is going to be, yo, this could be a for loop, or this could be a while loop instead. No, actually it's a different warning. This warning is, this could be a while loop. Why don't you have a while loop? That doesn't make sense. And same with y. If we declare y, if we want access to y after the loop, we're going to have to declare it before the loop. Just like val was declared before the while loop, so it was not destroyed when the while loop ended because it wasn't created after the while loop started, so it wasn't in that code block. So we have access to val after the while loop ends. We can do the same thing with the for loop, declare our variables before the loop starts, and then when the loop ends, those variables aren't destroyed because the variables were not declared as part of the code block for the for loop. So this is why in our traces we're very careful. If a variable is declared inside of a code block, put it in a code block, because that variable is going to be destroyed at the end of that code block, and we want to capture all that behavior in our traces. So now when we run this code, it runs fine, and it's going to print the final value of x, which was 5, even though 5 wasn't printed to the screen as part of the loop. I am printing it at the end, and we can verify that x did actually reach the value 5, so we did the right thing in our trace. And the y of 7, it was just assigned 7 and printed, so that one's less interesting. But y was not destroyed in this case because it wasn't declared inside of the code block. But we can update it if we want to say y equals 10. We can change it from inside the code block. So we can reassign variables inside a code block as long as they're not declared inside the code block, meaning that we specified the type and created the variable for the first time. If they're not declared inside the code block, then they are not part of that code block, and they do live after that code block ends. So we can reassign, that's fine. We're reassigning x also here in this modified example. But if they're declared inside the code block, they're destroyed along with the code block. Okay. Oops. Alt tab. Go over here. I'm going to take a brief break, like less than a minute here, and we'll get into the next lecture. All right. And we're back. All right. So let's jump into some data structures. Okay. And it was Control-Shift-P. Okay. Array list and hash map. So these are... Oh yeah, I want to talk about memory first. But array list and hash map, these are going to be our two data structures that are going to make us, are going to get us through this course. These two data structures are going to be our mainstays. This is effectively list and dictionary in Python. So everything you know about those two things, most of it at least, except maybe strange plus equals behavior, is going to transfer over to these. Array list does not have plus equals behavior in Java. So these two are going to get us a long way through the semester. We're going to keep using them even after we learn our other data structures, our linked list, trees, and graphs are actually made out of array lists and hash maps. So these two are going to be very important all semester. And we're going to need to learn the syntax of how to work with them. But first, a little intermission. I don't know, some backstory. I don't know. I'm blanking on the word here. But let's talk about memory a little bit. This is something that I hope they cover in 115. I'd be surprised if they didn't. So hopefully this is a reminder. But if not, I do want to talk about what memory actually is. Because we talk about memory, stack memory, heap memory all the time. Let's talk about what we're even talking about with there and get these memory traces related to the real world a bit. So when we say memory, we mean random access memory, or RAM. These are RAM sticks in our computer, and you know what these are. You know what memory is when you're purchasing a laptop or a desktop, any machine. One of the specs you're going to look at is how much memory does it have. How many gigs of memory do I have in this machine? And that's what we're talking about when we talk about memory in our memory diagrams, in our traces, is the same thing. We're talking about that RAM, your RAM in your machine, and how our programs are going to effectively use that RAM. And this RAM is essentially a giant array that can index memory addresses by indices. And those memory addresses are bytes. So we can store bytes and we can retrieve bytes by index. And that's how we're using our memory. So first, when we start a program, our program is going to talk to the operating system. And I'm saying this generically for any program, but this is because you do have to go to the operating system at some point. In Java specifically, our program is talking to the JVM, the Java Virtual Machine, and the JVM is talking to the operating system. So we can have an intermediary there, but at some point, memory has to come from the operating system. The operating system is what controls memory usage. So at some point, our program's request has to make it to the operating system. We're going to say, hey, operating system, I need some stack space. Because I'm about to run and I need some memory to be able to write things down. Operating system says, okay, here you go. Here's a chunk of that RAM that you can use for your stack. And we have to stay within the confines of that space that the operating system gave us, which is usually pretty large. I have it shown fairly small on the page here on the slide, but we get quite a bit of memory. Like, we usually don't have to worry about running out of stack space. But the way I have it visualized here, it looks kind of small. And anything before that chunk of memory and after that chunk of memory, we are not allowed to access. It might be used by another program. It might not. It might be available, but it's not available for us. We are not allowed to go outside the bounds of that memory. We're not allowed to do it. We have to stay within what the operating system gave us for our execution of the program. And the way we use stacks, the stack memory, is that it's one continuous block of RAM, and when we add things to the stack, we are using the next available memory addresses for whatever variable or stack frame we're adding to the stack. And this always happens in a last in, first out manner. So if we're adding a code block to the stack, that code block is removed. If it's removed, those values, those memory addresses are freed up for the next values that are going to be added. And a stack really is a stack of stack frames. So when you add a new stack frame to the stack, you're adding it to the top of the stack, and it's only the top stack frame that's allowed to be accessed. So whatever is the last method call that was called, its stack frame is the active stack frame, and once it returns, it goes back to whatever stack frame called it. That's the new active stack frame. So it is really like a stack of stack frames. The top one is active. Once it returns, it goes back to the previous one. And once all the stack frames return, program's over. The bottom of the stack is always the main stack frame in Java. So it is really a literal stack of stack frames. In our memory diagrams, we draw this upside down. So the top of the stack is actually the bottom stack frame visually in our traces. So it is like an upside down stack. But that really is, and that's why it's called a stack. It's because it follows the stack structure. We will not next Tuesday, but the following Tuesday, when we talk about linked lists, we will actually talk about the stack data structure and talk a little bit more about what last in first out means, and then I'll refresh stack memory and make that connection again. But that's what stack memory is, a stack of stack frames. We also have heap memory, which we haven't used in a memory diagram yet, but guess what? We're gonna today. So let's talk about what heap memory is. Heap memory is where our array lists and hash maps are going to be stored. So that's why I want to talk about this right now. And heap memory is much more dynamic. When you first start your program, you don't have any heap memory. There's no, or heap space. Sometimes they'll say heap space, but you have no heap memory allocated for your program. But you can ask for heap memory at any point during the execution of the program. So it's much more dynamic, where your stack is, here's your stack, this is what you have for the entire execution of your program. You're never going to get more stack space. You're never going to lose stack space. It is what it is for the entire run of the program. Heap space, you get as much as, not really as much as you want. I mean, eventually the operating system is going to say, eventually the operating system is going to say no. That point might be once all, you ran out of RAM on your device, or and swap space, I guess. But it is more dynamic. You can ask for heap space whenever you need more heap space. So if you're going to create a data structure, you're going to say, hey operating system, or JVM, hey operating system, I need enough space to store this array list. And the operating system is going to find a space in memory which isn't going to be where your stack is. It might be completely, very far away from where your stack is. It might be on a whole different RAM stick entirely. But it's going to find a spot for the memory that you asked for. You're going to ask for, hey, I need 100 bytes. And it's going to say, okay, I got a chunk of 100 bytes over here. It's going to find a chunk of RAM for you and give you the memory address of that RAM. It's going to say, I found a chunk of RAM for you. It's over at memory index 8302 or whatever. That's where the space is allocated. So you take that memory address, and then the next 100 bytes in this example. That's what you have access to. And again, just like the stack, you can't access any memory that hasn't been allocated for your program. And with heap space, we don't care where the operating system found that space. We just care that they did find the space, and that they gave us a reference to that, space, which is the memory address. They said, here's where you can find the space. In our memory diagrams, that's going to look like OX100, OX200. Those are the references where the operating system found memory for us when we asked for heap space. So we only store these references in our variables, which is the location of the memory that the operating system gave to us. So that's a high-level overview of heap space. And let's talk about, oh, did I get rid of my example? Oh, no, I have it in, I was expecting an example there. I have it in the linked list lecture now. I used to have it right here, but I forgot I moved it. Makes more sense when we talk about linked lists. Just because we have more background, I don't want to hit you with too much heap stuff right now, because it's it can be a lot all at once, especially when we're learning so many other things right now. Let's focus on array list and hash map. But if you do have questions about the heap, I'd love to talk about it more. So let's talk about array list. This is your list in Python. So coming from 115, you know all about lists in Python. That's pretty much mostly the same data structure as array list. It's your arrays in JavaScript. If for some reason you're coming from JavaScript, we used to do JavaScript in 115 alongside Python, which is why I have this in the slide. This is your vector in C++, if you're coming from C++. It's your basic sequential data structure with indices 0 to n-1, where n's the number of values in the data structure. That's every programming language is going to have one of these. I'm sure there's some out there that don't, some that I'm not aware of, but any pretty much any programming language is going to have this data structure or some form. Some only have the base form of arrays, just plain old arrays, but they're going to have some sequential data structure within the indices starting at 0. Except MATLAB, where indices start at 1, because MATLAB's weird. So that's the data structure we're talking about. No matter how you got to this course, whatever you took to as the prereq to get into this, you've seen this data structure. So let's talk about the Java specific stuff. Mostly syntax is what I want to highlight here. Because you should all know how this data structure works. We just got to talk about the syntax of how Java makes it work. And there is actually quite a bit to talk about with Java's syntax here and how exactly it works. So first, we have our first import statement. Like I said, outside of a class, you can only have 2 things, packages and import statements. Here's the second one. A lot of classes in Java we can use just without any questions. For example, we've been using string and system. We've been using these two all along. I didn't even really mention them because we don't have to do anything special with them. We can just use them. We can just use strings. We can just use system to access out, to call print line. We can just do that. With array list, we can't. With array list and hash map, these are not auto imported, so string and system and integer here, a few others are auto imported. You just don't have to import them. Java, the developers said, you know what, so many programmers are going to use these things in like every program. Let's just auto import the ones that everybody's using all the time. And they draw the line at array list. Array list, they're like, nah, not everybody needs that. So if they want array list, they are going to have to import it. Array list does come with Java, but we don't want to have to load the class if we don't have to. For performance reasons, if we're loading the entire Java library in every program that we run, it's going to take a while just for our programs to start up because there's just so much stuff in there. So beyond just a few classes, the Java developers said you can pick and choose what you want on a per file basis. So we're going to import array list, load this class, so then we can use it. And we can infer a few things that may or may not be interesting to you. But java.util.ArrayList, this is the fully qualified name of the class. Java.util, this is going to be the package. And then ArrayList is the class name. So if we wanted to find the ArrayList code, if we go through the Java library, the JDK, we're going to find it in a directory named Java, in a subdirectory named util, and then in a file named ArrayList.java. We know that because Java enforces package structure and file names matching class names. So we know exactly where to find this ArrayList code if we want to look at the source code for the ArrayList class. Oh yeah, and all our primitives, int, double, boolean, were the 3 primitives that we've seen. Okay, so now that it's imported, we're allowed to use it. If we forget this import statement, as soon as we start using array list right here, we're going to get errors because Java doesn't know what an array list is if we didn't import it. When we create a new array list, we do have to use the keyword new. So we're going to say new array list, and then we have to have these angle brackets here. I'll talk about them when we get to the variable side, and it's not even 9:30. I'm already losing it. And a parameter list. So this parameter list is empty right now. For now, you can just know that this is calling a method. This is a special method called a constructor that's being called. When you use the keyword new, you're saying, hey Java, I want to create a new object. That's going to allocate space on the heap. It's going to ask the operating system for heap space, do all that stuff. It's actually going to ask the JVM, but since we're in Java. But it's going to ask for heap space, enough to store this new array list, and then it will call a special method called the constructor. The reason we need to know that right now is just that we are going to have parentheses here because we do have to have an argument list that matches the parameter list of that constructor. The constructor we're calling has no parameters, so we're giving it no arguments, but it is still a method call, so we have to have our argument list even though it's empty in this situation. As always, more details to come in lecture 4 next Tuesday. On the variable side, we do have to specify what we call a type parameter. So these angle brackets are specifying type parameters. On the right-hand side, it was one of my bullet points, but I'll talk about it here. On the right-hand side, we can specify the type right here, which is integer in this case. So we can put integer right here, but Java doesn't force us to do that. Even if you do put it there, IntelliJ will give you a warning that says, hey, you didn't have to type that. Like, you want me to delete that for you? So we don't have to specify it twice, but we do have to specify for this array list what type it's going to store. So an array list, unlike an array in Python, cannot mix types. So this is Java taking that strong typing seriously. Java doesn't just say, okay, your variable has to have a type, and that type is array list. For our data structures, the data structure also has to have a type that it can store. So this array list can only ever store integers. And if I try to put a double or a string or a boolean into this array list, it's not going to work for me. Because this array list can only ever store integers. It can only store integers. And you do have to specify a type. You have to specify what type that array list is going to store, in this case, integer. So whenever I add to it, it better be an integer. And I do need, even though this is an empty type parameter list and an empty argument list, I guess it'd be type argument, then even though they're both empty, we do have to have both lists on the right-hand side as well. So that's everything that's going on in this one. But you also might notice this, it's a lot. Java's a lot. It's verbose. There's just a lot going on here. So even just creating a list where Python would just be R1 equals open square bracket, close square bracket, and easy day, we're done, we have a list. Not so much in Java. For good reason. A lot of good reasons why Java's like this. Python, if you try to write large programs in Python, the lack of all these things will get you in trouble and will make programming quite a bit more frustrating when you get those large programs. 116 is all about writing large programs, so we pull in Java and we learn all these little things like this and we write better code. So it is all for good reason, but there's a lot to explain on the Intro to Java lectures as a result. Okay, but notice that I'm saying type. Oh, I didn't really introduce that. But these type parameters have to be class types. This is where the difference between our class types and our primitives is going to come into play. So a class type is any type that starts with a capital letter. Up until right now, this example, the only class type we've seen was string, and I kind of said, hey, look, it's a capital S. Ain't that neat? We'll worry about that later. Well, it's later. So the capital S means that there is a class that defines this type. Capital A array list, there's a class out there somewhere. It's actually in the Java util package called array list that defines this type. String, there's a class string, there's a file string.java that defines the string class, that defines everything that is a string class, an array list class, but not with primitive values. Any of our types that start with a lowercase letter, like int, this is a primitive type, meaning there is no int class. There's no class that defines all of the behavior for an int. An int is strictly just a value. It's a special value in Java where Java knows how to represent int values in binary, and it's going to store just the value of that int in the variable. Same with double, same with Boolean, the three primitive value types that we've seen. So the reason we're talking about this right now is that your type parameters cannot be primitives. They have to be class types. So what happens when we want an array list of ints? Well, we can't do it because int's a primitive, but Java does give us an option here. Java gives us class types that match the primitive types. So there is a capital I integer class that behaves just like, for the most part, just like an int, except it is a class, which gives it a lot of extra functionality for our purposes. We're not really going to use much of it, but it does give us a lot of extra functionality on top of an int, which is just a value, just a binary, 32-bit binary value. An integer is a full object on the heap with methods that you can call. If I have a capital I integer, I can say dot, and I'll have a whole list of methods that I can call on that integer value, on that integer object. So array lists and all our data structures can only have class types, so we have to use these class type versions of our primitive types. So capital I integer, capital D double, capital B Boolean, these are different types than their primitive counterparts. So we can have an array list of capital I integer, but we cannot have an array list of lowercase I ints. Doesn't work. And Java is usually pretty good at converting between these. So for example, I have int x here, and then I do 10 minus x. These are both ints, but then I add them to my array list of integers. Java's going to convert these ints into integers for me. And same with this, I have an int, lowercase I int variable, and I'm going to plus equals whatever I get out of the array list. This is going to be an integer, capital I integer, and I'm going to add it to a lowercase I int and then store it in a variable of type lowercase I int. And Java's going to do all that conversion for me too. It's going to convert the integer into an int so I can perform that math and store it in the variable. Most cases, you just don't have to think about this. It's called auto-boxing, switching between the primitive types and their class type counterparts. But sometimes we do. The rule of thumb for 116 is always use the primitive types unless it's a type parameter. Type parameter is the only situation where we have to use the class types. In every other situation, use the primitive types. Always. And especially when it's the return type or a parameter of a method, this is where it's really important. If a method, like in all of the homework assignments, all of the tasks, if a method returns an int, it's going to say in the assignment, this method returns an int. I will never say this method returns a capital I integer or a capital D double. I'm never going to put that in an assignment. Well, all the assignments are already out. None of them have that. None of them will do that. They will always return the primitive type. So when you read that in the assignment and it says this method returns a lowercase d double, make sure it returns a lowercase d double. Like just do it. Just do that. The reason I say it like that is every semester there are numerous students who will return a capital D double in that situation. They'll submit to Autolab, and Autolab's going to have all kinds of errors because it's not expecting that return type. And in that specific situation, Java will not autobox. So if you have the wrong return type and you submit to Autolab, the way Autolab's set up, it's expecting a lowercase d double and you give it a capital D double, it's going to blow up. It's going to be errors and you're not making progress on that task. I don't know why students ever feel the need to put capital D double, capital I integer, capital B Boolean when the handout clearly says not to do that. But anyway, just don't be that person. Don't be that person coming to office hours and saying, God damn it, I just spent 3 hours on this and that was the issue, and I pointed out in like 2 seconds. Just don't be that person for your own sake. You're going to waste your own time. You might miss an expected deadline. Don't miss an expected deadline because of that. It's such a dumb way to miss an expected deadline. But I see it every semester, and it's frustrating. It's frustrating for me. It's more frustrating for the students, but it's frustrating for me as well to see it because it's such a silly mistake to make. Because I mention it right here in lecture. It's in every homework document in the sense that it doesn't say return an integer with capital I. But I have just a lot of built up frustration from seeing students do that every semester. I'm frustrated for them, not at them, for what it's worth, to be clear. I'm frustrated for them because I don't like seeing students waste their time. It's always a tough office hour visit when I have to see them. I spent so much time on this. I'm like, you didn't have to. I don't want you to. I don't want you to waste that time. Okay, so moving on. The methods, now that we've set up, we had a lot to talk about with this one line, but I don't have much else to talk about. It's just the syntax. We cannot use this bracket syntax like we did in Python and most other languages. That doesn't exist with ArrayList. We have to use .get and .add. So if you want to add a value, .add, that's going to add your value to the next available index. So if I have no values in my array list, this is going to add in index 0, index 1. And then once I have one value in the array list, it'll add at index 1. Once I have 2, it'll add at index 2, etc. And get is going to take an index and return the value at that index. So instead of where this would be array of some index equals, and this would be array of some index, using where I'm saying of using the square bracket notation. We don't have that with ArrayList. We have to use .add and .get. And for what it's worth, .add can take an additional parameter which says add this value at this specific index, which is something that'll come up later in the semester. You can use it now. It'll be add index then value if you want to use that, if you have a situation where you need to use that. Okay, now we're ready for the memory diagram. Okay, I'll tab over to IntelliJ, copy this, go to UB Power, squash this, paste this. Let's trace this thing. Hide toolbar, full screen. Okay. Every Java program starts with a main method. I can stop emphasizing that now. You've seen it enough times. And our first line, we have our constructor call, all this stuff that we just talked about. I'm not going to reiterate all of it. But we need to talk about what happens in memory when we create this. If you're coming from 115, you know what's coming. If you're not, well, actually, I already foreshadowed it in the slides. But whenever we see the keyword new is your clue. But whenever we have a class type that we're creating a value, I guess, of a class type, we're creating an object. I'm just going to start saying object. We're going to see that next week anyway. When we're creating an object of a class type, whenever we say new, we use the keyword new, we're creating an object of that class type. Whenever we do that, that object goes on the heap. So we're going to create our first heap object. When we create an object on the heap, every object is stored on the heap. Every object is in the heap. We do not store objects on the stack ever. We don't store objects on the stack. Let me do it right now, I guess. Let's get this out of the way. Strings are also stored in the heap, but we are going to pretend that strings are primitives because strings behave like primitives for reasons. They're immutable. I don't have to go down that whole rabbit hole. Unless somebody wants to know, it's probably not this early in the semester. But if somebody wants to go down that rabbit hole, I'll be happy to. But a string is on the heap, but they behave the same way as primitive values, just like ints and doubles. So we, in 116, pretend that they are primitives by putting them in our variables as values, even though that's not actually how they are represented in memory. But since they behave that way, they don't behave like references like we're about to talk about, we're not going to bother creating that, because strings are really weird. If we actually traced strings the way they behave in the computer, our memory diagrams would be many times more complex. It would be like just going through this example, we don't even use many strings in this one. Just right here, here. Oh, we actually use a decent amount. All those strings would be objects on the heap, even though we don't store them in variables. We would have to create all those objects on the heap. Like this line right here would actually create a string on the heap for total colon space, and then another object on the heap for the total, this value as a string, and then another one, a third object for their concatenation. So just this print line would create 3 objects on the heap. And no, we're not getting bogged down in those details. We're not going to bother. So with that one exception, which isn't an exception, it's just an exception in the way that we're going to do our traces, just to simplify the traces. And then in 220, they can straighten you out and they can curse me out and say, Jesse told you strings were stored by value. What the hell? Now I gotta unteach you that and reteach you the right way. They can do that in 220. We're not going to get bogged down in that in 116. We got enough other stuff to talk about. So other than strings, every time you see the keyword new, actually we don't use the keyword new with strings because strings are just really weird, but this is creating a new object. Anyway, so aside from strings, whenever you create an object of a class type and you see the keyword new, that's going to be an object on the heap. Every time you execute a line of code that has the keyword new, you're creating a new object on the heap. When you create an object on the heap, we're going to put the type of that object. So we have an array list here, and then we're going to have all the variables for that object, which we don't have any variables in this array list right now. But we created an array list, and we got a reference right here, OX100. We're using this to say that this is where we got heap space. Then when you actually run your program, you're going to get some random place in the heap. We don't know where it's going to be or anything. For tracing, the tracing tool will always have your first object at OX100, your second one at OX200, etc. So it's going to go just in order like that, just so we have some numbers to represent. You can change these if you want. There's no real reason to, but you can change this number, this reference if you want. The value here doesn't really matter as long as you're consistent. And when I have a variable that's going to store the result of a constructor call of object creation here, what this resolves to is the reference only. So the variable R1 is only going to get a reference to the object that was created. So you can change this number, that's fine, as long as you change it in both places. As long as you're consistent, this number doesn't actually have any intrinsic value to us. If I put OX999 here and OX999 here, that's fine. We just need to know that R1 refers to this object on the heap. And having this OX100, I follow the reference to OX100 in memory, And now I know where to find that object in heap space, in heap memory. So whenever we have a variable that looks like it stores an object, it does not store an object. So this we always think of, and I'll even say it just because it's easier to say, that R1 is a variable that stores an array list of integers. That's not really accurate. Array list is of type array list of integer, but what it stores is only a reference to an array list of integers, where that reference is the memory address of where in memory there is an array list of integers that exists out there somewhere else, which happens to be at OX100 in this example. But R1 only stores that reference. The instructions, I like to call it a roadmap. It stores a roadmap of where to find the object. It does not store the object itself. A reference to the object. Okay. So coming from 115, that should be review, but holy goodness, it's important. We need to understand that concept. And it will be important throughout the entire semester. And there's 0% chance you can get through the OOP quiz without understanding references. So I'll talk about references a lot. But that's your first intro to it, or first reminder of it. Okay, then we hit our loop. We do need our code block here because x is declared inside of the loop. And x gets the value 0. X equals 0. We just did a few loops, so I'll go a little bit quicker through this one. 0 less than 4, so we're going to execute this line, r1.add. This line I have to focus on. The loop stuff I'll gloss over a bit more. r1.add. Whenever we see the dot operator, what this means is that r1 resolves to a reference. So we effectively have OX100 dot. OX100, the dot operator means, hey, look, I know you're a reference, and I don't give a damn about references. Nobody cares. Nowhere in your code will you ever care what this value is. That's why we can change this value to 999. As long as we're consistent, that's fine. We don't care what the value is. The dot operator says, hey, I don't care. I just know you're a reference, and I don't care what you are, what your value is. Just take me to your damn object. So the dot operator means follow these instructions, go to that location in memory, and take me to that actual array list in this case. Take me to that array list. So dot means take me to your object. You are a reference. You refer to an object. Take me to your object. So R1 dot means now we're over at this array list in the heap. And then when we call the add method, we're calling that add method on this array list because we followed the reference to the heap to get to this array list. And then the value we're adding is 10 minus x. This is a separate expression, so we're no longer at the array list in the heap. We evaluate this from the stack frame again. We always start at the stack frame to evaluate an expression. And one way you can think of this is what's inside the parentheses is evaluated first, your PEMDAS stuff. So this is evaluated first, even though I'm doing it, I'll always do it out of order for the traces. But this has to be evaluated first, which is from the stack frame. So 10 minus x, x is 0, so that's going to be 10. So we're adding the value 10 to this array list. Add will add that value in the next available index. There's nothing in this thing, so the next available index is 0. That'll be kind of the name of the variable. It's a little weird with array lists. Array lists are a little special here. But the name, 0, and then 10. We hit the end of the loop. Increment x. 1 less than 4 is true, so we do it again. R1 dot add the value 10 minus 1, so we're adding 9 at index 1. End of the loop, increment x. 2 less than 4 is true, so we do it again. R1 dot add at index 2, we're adding the value 8. we reach the end of the loop, increment x to 3. 3 less than 4 is true, so we do it again. We're going to add at index 3 the value 7. We reach the end of the loop, increment x to 4. 4 less than 4 is false, so we do not add 6. We're not adding 6 to this array list. We are done with the loop, and we move on. Printing to the screen. When we print an array list to the screen, for what it's worth, this is the syntax. We're going to have brackets and then comma separated values. If you don't print in the exact right format, by the way, I don't really care that much. As long as you can demonstrate understanding of the learning objectives. I feel like I said that a bunch of times by now. But if you don't memorize the syntax here, that's fine. It's pretty straightforward syntax, especially coming from Python. It's the same syntax there, so it's probably just going to stick anyway, but if it doesn't, it's not something I'm not gonna lose sleep over that if some of you don't have the right syntax there. But for what it's worth, that's the right syntax. And then array, we're creating a new variable R2 of type array list of integer and assigning it the value R1. What's going to happen on this line? Very, very important line, and I promise you I'll have a line like this on the OOP quiz. On all 4 of them, there's going to be a line that looks just like this. Some class type variable equals another variable. What happens here, first of all, what happens with any assignment operator, we resolve the right-hand side. If the right-hand side is a variable, what it resolves to is its value. That's it. So R1, I look for R1, its value is the reference OX100. Its value is a reference. So whenever we have an assignment like this, what we get is the value, which is whatever the hell is sitting next to that variable on the stack. It happens to be OX100. R2 gets the value OX100. And that's it. That's all that happens on this line. We do not see the keyword new, so we are not creating a new object on the heap. This does not make a copy of array 1. It doesn't make a copy of the array list referred to by the reference stored in array 1. It doesn't do any of that. It just copies the reference. So R2 has the reference OX100. R1 has the reference OX100. They both refer to the same object. So R1 and R2 are 2 variables that store references to the same object, meaning if I make any changes to one of them, it will make changes to both of them because they're both referring to the same exact object. This example isn't going to make changes to the object like that, but we will see that throughout the semester. So if I print array 2, guess what it prints? 10, 9, 8, 8, 7. If I can type correctly. The exact same thing. R1 and R2 refer to the exact same object, so when I print them to the screen, I better get the exact same thing. It's the same exact object. Then we have a method call, so let me get my variable total, my stack frame sum, which is going to return to total. Sum takes a parameter called RIN. And we're going to do this the same way we did with our primitives, where our primitives were just passed by value. We're going to pass a reference here. So RIN, array list integer RIN equals R1. This is the same exact thing we just did in this line, except the assignment is split across a parameter declaration and a argument of a method call. But it's the same exact thing. So RIN gets the value of R1. R1 is OX100. So this gets OX100. We're ready to run the method. Out equals 0. For, we have a code block. X equals 0. X less than array in dot size. Its size is 4 because we have 4 values, so we're going to do RIN dot size. So we're asking this object for its size. It says I have 4 values. It's got 4 values. So size is 4. So 0 less than 4 is true. So out plus equals rn.getX. So rn dot, we're at this array list right here. We're calling get. And the index we're getting the value of is x. This is a separate expression, so we go back to the stack frame to evaluate it. X has the value 0, so give me the value at index 0, which is 10, and add that to out. So out plus equals 10. Out is 0, so 0 plus 10 is 10. We hit the end of that loop. Increment x. 1 less than 4 is true, so we're going to do it again. We're going to go rn dot get x. X is 1, so get the value at 1, which is 9, and add that to out. So out plus equals 9. 10 plus 9 is 19, and reassign it to out. Increment x. 2 less than 4, that's true. So we're going to do it again. Array n dot get 2 is 8. So 19 plus 8 is 27. Increment x to 3. 3 less than 4 is true, so do it again. We're going to add 7 to out, and we're going to get 34. Get to the end, increment x again. X is 4. 4 less than 4 is false, so we're done with this code block. Cross that out, and then we're done with the method 2. We're going to return out. Out is 34, so cross this out and return 34 to total. And our last line, total is total. Print total 34. And that's the end of the program. That's the end of that trace. And I want to go to this one. All right, so we did our trace. Again, same exact stuff in these slides, just a different format. And we're ready to talk about hash maps. And actually, we got plenty of time, right? 38 minutes. We should be able to finish this with the memory diagram and everything. So hash maps are our key value stores. And we already did the IntelliJ tutorial, so we got this. We got everything I want to do today. And we'll be on track for unit testing on Tuesday. So this is our key value store, where we're mapping keys to values instead of values at integer indices starting at 0. We can map objects to other objects with our key value store. This is just like your dictionary in Python. Object if you're coming from JavaScript. I think it's just maps in C++ if you're coming from C++. Are key value stores. So with this, order does not matter, and you can't have duplicate keys are the two things to remember from whatever CS1 you took. Order doesn't matter, so when we throw things in a hash map, we aren't getting them in the order in which we inserted them. We're getting them in a randomish, it's not literally random, but it's a randomish to us order that we're getting those values in. And we can't have duplicate keys, so if we add in a duplicate key, if I add in Alan 17, then Alan, I don't want to change Alan's number, but if we add in another key, actually there are 2 Allens on the team. I forget the other Alan's number, but if we add in the other Alan, it's going to override the previous one. We don't want that, so we got to be careful about duplicate keys. If we add in another value, another key value pair with the same key twice, it will override the previous one that was added. Which sometimes we do want to do if we want to update the value at a key. we just insert a key value pair with the same key again, and it'll update the value. Okay, so syntax. I have much less to say about this one than ArrayList because most of the things are the same, like the import statement. I don't really have to talk about import statement again. There's the package Java util, just like ArrayList, except there's another class called hashmap in that package. We're going to import that thing. So we got to import it before using it. We have two type parameters now because the keys and the values can be different types. Here I'm creating a hash map of string to integer is the way I would say this and the way it would be described in a programming task. So we're mapping strings to integers. The keys are strings. The values are integers for this hash map. So we have to have every key that we put in is a string. Every value is an integer. So we can have different types between key and value, but every key has to be the key type and every value has to be the value type. And we separate those by a comma. This is a type parameter list, or a type argument list, I suppose. And we can have as many of these as we want. This is the most we'll see is 2 for hash maps. If you have more than 2, there's probably a better way of reorganizing the code. And put, if we want to insert into a hash map, so put is going to take a key and a value, and get me the value at a particular key. It's really all the syntax for manipulating a key value pair that I want to say, a hash map. And then we have 3 different ways to iterate over these. This one is new, so let's talk about this. We have the for each loop, or as Java calls them, an enhanced for loop. But for each loop is kind of the more generic term for these things. So that's the one I like to use, is the for each loop. But Java will call them Java documentation. If you see enhanced for loop, that's what they mean. They mean a for each loop. This should be really familiar for you coming from 1.15 because this is the only type of loop Python has, the only type of for loop Python has. So this is much more familiar to you from Python. If you're not coming from Python, this is declaring a variable and then iterating over all of the values in a data structure and storing them one at a time in that variable. So in the example we just saw with an array list where we were iterating over the indices and then accessing the value for each indice, instead, what we're doing is iterating over the data structure directly, doing the same exact thing. Well, it's almost the same exact thing, but we're doing it a lot cleaner. We're just saying for string key in this data structure. Just iterate over all the values of that data structure and put each value in this variable key one at a time. And we can use the same syntax with our array lists as well. So the previous example, we could have said, let me not get back to it, but we could have said like for int x in array in. We could have iterated over the values like that. Sometimes you do have to iterate over the indices for an array list, so I wanted to make sure I showed you the way to do it with that, iterating over the indices. But you can just iterate over the values too if you don't need the indices. With a hash map, we have two different, there are 3, but I don't like talking about the third one, ways to iterate over the values, the information inside of a hash map. 1, you can iterate over just the keys with key set. 2, you can iterate over just the values with .values. Or there's a third one where you can iterate over the entry set and iterate over keys and values simultaneously. I personally don't like that one, and I think it's more confusing in a 1.16. Still confusing for me to even use, so I just don't. It's not that confusing objectively, but it's one more thing, one more piece of syntax that I have to remember, and I don't feel like remembering it, and I don't feel like looking it up every time I have to use it to remember what the exact syntax is in Java. So what I'll do is iterate over the key set, and then the first line of my method, I very often have loops like this, I'll iterate over the key set, and the very first line of my loop is going to be accessing the value at that key. So now I have both key and value, and then I can do whatever I need to do with the key and value, instead of trying to work with entry sets and forget the syntax and look it up every time. I don't like doing that. I don't like bothering. If I can cut down my memorization, I will. If I can cut down the things I have to look up. Programming is already too much looking up stuff. I don't need to look up more stuff. But the reason I say this is if you want to use entry set and you understand how to use it and you can memorize the syntax and stuff, go for it. I don't care if you use it. But it's unnecessary, in my opinion. Okay. Oops. I already got ahead of myself. I was still on the for each loop slide. But yeah, key set, values, or iterate over key set and access the values. Because you will, like for example, the third method on task 1, where you're finding the best key, you're going to want to iterate over the keys and values simultaneously. So if you use this third flavor to get both of them, you're doing a max on the values, but once you find the max, you have to store the key and the value for that max. So you're going to need to iterate over the keys and values simultaneously. And similarly, sometimes you have to do that with array list, iterate over the indices and access the values like we did in the previous example. So if I have a question that says like, give me the index of the max value, I don't have that index. That's a 115 thing, and task 1 is the only thing with 115 stuff on it. But we'll have similar things where you'll need the same functionality. You'll need the actual index of the array list values. And a memory diagram. So this is the last thing we need to get through today is this memory diagram. Where the hell did IntelliJ go? Trash can that. All my hard work just gone like that. Let's trace this thing. We got 28 minutes. We got this. And we might actually get to that example that I just flashed for a second there. Full screen. Let's do this. Alright, every Java program starts with the main method. We're going to create a hash map called bills. That's an object on the heap. We see the keyword new. That's always your clue. If you see the keyword new, you're creating an object on the heap. If you don't see the keyword new, you're not creating an object on the heap. Very straightforward, very cut and dry. Don't make the mistake of seeing assignment by reference and creating a new object on the heap. Just don't do it. And the next line, bills, and that resolves to constructors. When we see new, this always resolves to a reference to the object that was created. So this resolves to OX100 in our case, and that's what's stored in our variable. And then bills dot put Alan 17. Bills dot put colon 0. And we're going to print. I'm going to copy this so I don't feel like typing it all. What is Alan's number? And I always get this question. It's just a little formatting thing. Kind of tempted to change this just so I don't have the question every time, because it's nothing that will affect your grades on the traces if you miss this one. But it is a nice little tip/trick, so I guess it's still worth saying. But I'm using print here and then print line in most other cases, and then print again here. The difference between print and print line is print line will give you a trailing new line character. So print will just print the text itself with no new line character, meaning that the next thing that you print, which is bills dot get Alan 17, is going to be printed on this line up here, because this had no trailing new line character. The 17 does have a trailing new line character, so the next thing that's printed will be on the next line, which is just printing the entire hash map itself. So the hash map syntax for hash maps is going to be, ooh, I do actually forget if, I don't think the strings are in quotes in this situation. I could be wrong, but Alan equals 17. We'll find out. We'll go to IntelliJ and find out. Coleman equals 0. Actually, I want to go to IntelliJ right now. So this is the syntax. We have braces and then equal sign separating our key value pairs, which is not the format I wish they used, but it's fine. We'll live. I wish they used colons instead of equal signs. Okay, yeah, no quotes around the strings. I was right. And if we go to the code and print this to the screen, we're actually going to see something a little bit different than what I did in the memory diagram. And this is, I guess, depending on how you look at it, an important point or not so important point. It's not so important for your traces, but important for our code. But it is very important that you understand what's going on here, the concept, to be able to be a stronger programmer. But what we got here is Coleman equals 0, Alan equals 17. What I did in my trace is Alan equals 17, Coleman equals 0. When you're doing your so hash maps, order doesn't matter, right? When you put your key value pairs into a hash map, I inserted Alan then Coleman. But when I printed to the screen in IntelliJ, I got Coleman then Alan, the reverse order in which I ordered these. And it's not just reverse, it's random-ish. It's actually based on the hash value of the keys. So the hash value of Coleman happened to be before the hash value of Alan. When you're doing your traces, I don't care about the order. Since order doesn't matter with hash maps, if you print them in any order, usually what I do in my memory diagrams, and what I'd recommend you do, whenever you have a hash map, just work with them in the order in which they were inserted. And just print them in the order they were inserted, iterate over them in the order they were inserted. That's fine. Just do it that way. We're not going to give you code that uses a hash map on a quiz where the order will matter, where you'll actually get a different result based on the order. So you can just choose whatever order you want when you're iterating over a hash map. Because the order is too unpredictable to be able to determine during a tracing quiz. So just any order is fine. All right, then we're going to iterate over the key set. So we have our code block. And this is just like the regular for loop, where the variable for the loop is going to be declared as part of the code block for that loop. We're going to iterate over the key set. So we're iterating over the keys, Alan, Coleman. For your trace, if you just go in the order in which they were inserted, that's fine. In reality, this will actually go Coleman then Alan, but we're not concerned about that. That's not what we're assessing on a quiz. I'm going to go Alan then Coleman. So key Alan, print to the screen. We get to the end of the loop. For a for each loop, when you get to the end of the loop, you're advancing to the next element in the data structure that you're iterating over. So we go to Coleman, print Coleman, and that's the end of that loop. And we don't have that other situation where like we go to the next value and everything. The for each loop isn't going to do that. We got to the end of the data structure we were iterating over. That code block's done. And that variable key is removed from memory. It is deleted, which we indicate by crossing out the code block. This is the first one where it's going to be important when we get to this third loop. But let's do the second one first. We have another code block. We have the variable value. It's going to iterate over the values of the hash map. So 17 then 0, which in reality will be 0 then 17. So the value 17, we're going to print that to the screen. 17, advance to the next value, 0, print 0. and then that's the end of the loop. We got through all of the values in the data structure, so we cross out this code block. And then we get to our third loop, and we're going to have an iteration variable key, which is iterating over the key set just like our first loop, so Alan. And then the first line of the loop is going to declare another variable. We have a type, then the variable, so we know we're declaring a new variable, just like string key as opposed to key or just value. We have the types, that means we're declaring a brand new variable. So we have a new variable named value, which is bills dot get Alan, so 17. And this is where it's important to know, or important why, really, variables are destroyed at the end of a code block. And it's very similar to what I said last time about stack frames being isolated environments. So in the code block, once the code block ends, the variables are destroyed, which means we can reuse those variable names. So the fact that this is allowed, key and value being in this code block, the fact that this is allowed is because key and value up here are no longer in memory, because at a glance it looks like I am declaring a variable key and then declaring another variable key, which isn't allowed. You can't have two variables with the same name in the same code block. That's not allowed. But since the first variable key was destroyed, we're allowed to reuse that variable name. And usually this is important, like we like to use I, for example, in a lot of loops. We have int I all over the place, and we can have multiple loops with int I because the previous I was already destroyed and removed from memory. So we are absolutely allowed to reuse the variables key and value, because key and value, the old variables, have been removed from memory because they were declared as part of a code block that ended. So we don't have to worry about variables have been removed from memory. So we don't have to worry about those. I gotta check my audio every once in a while. It does sound a little choppy. Getting mad at this mic. The audio's, I don't know, doesn't sound the way I want it to. And then we're going to iterate over the, so we got the first line, next line, Alan's number is, and that's a print, so there's new line character, and then value 17. We get to the end of the loop, we advance to the next key, and then get the value for that key and do the same thing. Coleman's number is 0. That's the end of that loop. Code block ends. We get to the end of the main method. Main method ends. And that's the end of our trace. I'm not going to mess with my mic right now. Any questions on any of that? We're going to be on it today. Y'all haven't asked a question since 8:41. I'm getting worried. That's why I had to check my audio. I'm like, hey, and I hope everything's working. I hope they're hearing me at least. It's always frustrating to have to throw away 2.5 hours of lecturing for a technical issue, especially. Hey, what's up, Dave? Thank you for the confirmation. All right, I do feel better knowing that the stream's working. And that's the last content I needed to go over. So we are caught up. We're ready for testing on Tuesday, next Tuesday. And let's go over some of the things here, just hitting some of the points that I wanted to make, that I did make, I should say. If I do int value equals 0 right here, I can, again, reuse this variable value. Even though it was already used twice, those are both destroyed already. They're no longer in the code blocks. But in normal circumstances, if you declare a variable 2 times, you're going to get an error. You can't have a duplicate variable with the same name in the same code block. It's not allowed. But since, or in the same stack frame, sorry. But since all these key that was destroyed, I can reuse key because the previous key is no longer in memory. So we can see the actual effect that has of code blocks, of keeping track of our code blocks and making sure that that works fine. This is something you never had to worry about in Python because you never explicitly declare a variable. You use the same syntax to declare as you do for reassign. So if you try to declare, think you're declaring a variable twice, what you're doing the second time is actually just reassigning it. So Java, since you do have to specify the type when you declare, and there's two different syntax, two different ways of declaring and reassigning, it is something we have to worry about. It is not worry, but it's something we have to be aware of. And again, notice that everything was backwards. It was Coleman, then Allen. It was 0, then 17. It was Coleman, then Allen. It was Coleman, then Allen. The order is reversed here. Than the order that we put them in. And it's not just reversed. It's always going to be... Oh, damn it. It's always going to be that order. So if I insert Coleman first and run this again, I'm going to get the same exact result. Because the hash value of Coleman comes before the hash value of Allen. It's just the way hash maps work in Java. Okay. Does anybody have any questions? Because we're in kind of free territory, open-ended territory. We can fill us in with whatever. I can just talk about whatever I want to talk about, whatever I think will be helpful, but it's always better if you ask questions so I can know like exactly where you're stuck on the homework assignments. Actually, that is what I want to talk about. Left to my own devices. If I know where you're stuck, then I know how to better help you. So for task 1, the current homework assignment, the testing requirements, the actual testing, you can't quite do until Tuesday's lecture. So if you're ready for it, I'd recommend watching lecture 3 from last summer so you can at least get started on the homework. You don't want to go too long without getting started on this. But you can still write the methods. So let's go over the methods because we have everything we need to write all 3 of these methods right now. So the average method takes an array list of doubles and returns the average of all the values in that array list. So we want to go through the array lists, that averaging the values in a data structure. That's something you should all know from 115 or whatever your CS1 was. So just getting you used to the Java syntax of working with an array list. That's what this one's all about. So writing a method takes an array list of doubles, returns a double. Actually, we can show cloning too. And I'll always specify the edge cases. I shouldn't say always. There's a few times where I don't. But most of the time, I'm going to specify the edge cases. If the array list is empty, what should this return? And we're going to say just return 0.0. So on an empty array list, return 0.0. Is there a way to make an array list without adding everything one by one? Yes. And that's actually the example that I have in IntelliJ right now. If you use this syntax, arrays.asList, then you can add everything in one single line. So this, if I S out this input, this is going to, we'll see that all those values are in the array list all at once. So arrays.asList. Arrays is another class that's not auto-imported, so you do have to import arrays as well, which usually IntelliJ is going to be really good about that. So if I get rid of this, and I get rid of this, and I do arrays, and I hit enter.asList, and then whatever my values were, I don't remember. It wrote the import statement for me. So IntelliJ is usually pretty good about auto-importing, but if it doesn't auto-import, make sure you're importing arrays, which is, again, in the java.util package. And if we go like into the JDK, we have our root directory, which is called java.base instead of source. And then the Java package, the util package, and arrays, array list, a whole bunch of other stuff, and also hash map. We can actually see the classes that are defining these types that we're using. So there is a class called ArrayList in a file named ArrayList.java. Same with hash map, same with arrays. There's a class called arrays that has a method somewhere in here. That has a method named asList that takes a, the syntax is beyond us right now, but it takes any number of values of the type parameter and then returns a list of that type parameter. And then the ArrayList constructor can take a list as an input. And it actually does create a new array list for what it's worth. It's interesting. So that's the way to do that. The arrays.asList. And setting up and I assume you're asking that for setting up the test cases for the average method. Arrays.asList is going to make your life a lot easier. It's a lot easier to set up all the test cases. Sum of digits, this one I referenced during the lecture. You're given an int, and you want to sum up all the digits. So 123, it's 1 plus 2 plus 3 is 6. 57 is 5 plus 7 is 12. Negative 36, 3 plus 6 is 9. You have to handle negative values as well. For this one, this is where I recommend using modulo arithmetic. So take your value mod 10, and I'm pretty heavy-handed on my hint with this one because without hints, sum of digits can be pretty tricky. I see students trying to convert the digits into strings, and I don't know, just a lot of wacky stuff that people do. The intended strategy for this, because one, I just want you to get a good feel for Java syntax while remembering your concepts from 115 or whatever your CS1 is. So the intended strat for this is if you use integer division, modulo division. If you take any number and take modulo 10 of that, which is the percent operator, which is integer division, except instead of only giving you the quotient, it only gives you the remainder. So if I take this modulo 10, that's going to give me 3. It's going to give me exactly the ones digit of this number. So I add 3 to my running total, to my accumulator variable, because a lot of these are the accumulator pattern. I'm going to add 3 to my accumulator, and then what I can do is take advantage of integer division, and I'm going to divide this number by 10. If I divide this by 10, it's going to effectively erase the ones digit, and I'm left with 12. If I take 12 and modulo 10 that again, that's going to give me 2. I add that to my running total, and then I keep repeating the process. So I repeat that process again. I divide this by 10 with integer division, so I'm left with just 1. I take that modulo 10, add 1 to my running total, divide that by 10 again. I'm going to be left with 0. 1 divided by 10 is going to be 0.1. The 0.1 is erased, and you just get the 0. And at that point, once I have the value 0, I know I'm done. So how to set that up? There's a loop. You might want to do that while something is true. But that's the intended strat, is combining integer division by 10 and modulo division by 10. If you combine those two things, sum of digits falls right into place. And finally, best key. This one, we haven't talked about testing yet, but this is mostly a testing thing. One is just iterating over a hash map where you are iterating over the keys and values. So it's that third flavor of loop that we just talked about today. But the big thing is this test case right here. This is really the reason for this method is testing this test case. This is our first situation where we want to write tests for a method. We want to test a method where there's more than one correct return value. So on this input, you're returning the key with the highest value. Cat and dog are tied for the highest value. So the method can either return cat or dog. So when you're writing your code, you just break ties arbitrarily. It doesn't matter which one you return. Who cares which one you return? But when you're writing your tests have to accept either one of these, either cat or dog. So in the correct solutions in Autolab, the correct solution is going to return either cat or dog. It's going to return one of them. And your test needs to accept either one of them being returned, or else Autolab is going to say your test failed a correct solution, meaning that the correct solution returned a correct value, but your test said it was no good. So what a lot of Piazza questions and office hour questions will be on this one, because this does cause a lot of trouble, and trouble because you're learning something new, not like trouble, oh shit, I have to fix the assignment, but trouble because it's intended to make sure that you know this thing, because it's something you got to know. You got to know this. Is what students will do is use this exact test case. And by the way, when I give example test cases here, it's a pretty damn good idea to use these as the start of your testing. It won't always get you all of the testing. I think for this one, just coding up the sample test cases, I think does get you through the testing portion on Autolab. I believe. I don't think I left anything up to you to figure out, just because it's the first testing assignment and the first assignment overall. But anyway, when students write their test, they'll use this test case, which please do use my test cases, and their code will return cat, and their test case will say, make sure the return value was cat. And then they submit to Autolab, and my correct solution is going to return dog, and their test fail that correct solution. They say, dog? That's not right. I was expecting cat. And that's just not the way we write tests. That's not acceptable. So that's what this one is trying to tease out, is showing you that there can be multiple correct answers, and your test has to accept any of the correct answers. So your test has to say, was the answer either cat or dog? If it was either of those, then we good. But if it wasn't either of those, then we're not good. But don't check and make sure it's specifically cat or specifically dog, whatever, because students will do whatever your method, the way you wrote your method, whatever it returns, that's what students will write for their test cases who make that mistake. So don't just assert that it returned what your code returns. Assert that it was either cat or dog, or any of the correct solutions in general. So you can write all three of these methods today, just given what was covered in lecture. You can write all three methods, but if you're not ahead on the lectures, you won't be able to write the test quite yet until Tuesday's lecture. But again, I recommend getting ahead and writing the test cases ahead of time anyway. Because once next Tuesday hits, that's when things really heat up, because you're going to start having tasks pretty much every lecture that are due 2 days after lecture. So if you haven't been working hard this week, Tuesday is going to hit you like a friggin' truck. If you're not putting in your 24 hours this week, things are going to get rough next week. So ideally, you'll go into Tuesday with task 1 done and try to start getting ahead by watching the old lectures. I hope a lot of you are doing that. If not, Tuesday, we cover unit testing. It's going to be due Thursday morning. Thursday, we're going to cover classes. This is a huge lecture. Lots of really critically important stuff are covered in this one. Stuff we'll be using all semester. Classes versus objects and testing classes and stuff. A lot going on here. And program test 2 is where things start heating up a little bit in terms of programming tasks. Then program test 3, this is where a good number of students, the ones who let themselves fall behind in the first lectures, test 3 is usually where they start getting the Fs. This is where students really start dropping off and falling off. And then inheritance is historically the first. I shouldn't say first, but it's a step up in difficulty. Like test 1, like test 2 is harder than test 1. Test 3 is harder than test 2. Test 4 is harder than test 3. So you have this. The difficulty curve keeps climbing for these early tests, and then in my opinion, it peaks at 4 and levels off for tests 5 through 8. I think 5 through 8 are about the same difficulty, or 4 through 8 I think are roughly the same difficulty. There's a little bit of increases in here, but by that time you have a lot of extra practice too, so you should be growing along with the difficulty of the assignments. That's not necessarily true for the initial ramp up from 1 to 4. 1 to 4, each one's going to feel harder, but after 4, the intent at least is that the rest of the programming assignments don't feel harder to you. So if you're going into task 1 cold without having started programming task 1, if you're going into Tuesday like that, the course doesn't let up after that. It's just assignment after assignment after assignment, and a midterm. Like we throw a midterm in there. Like when you're doing tests 5 and 6 and 7 right around midterm time, it's tough. Luckily, we have a lecture off right before the midterm this semester, so the timing of that is actually pretty good. But there's the course is about to get pretty relentless, starting on Tuesday. So with that, I'll see y'all on Tuesday. If I don't see you in office hours, I have office hours after lectures at 2 to 3. Yeah, 2 to 3. So if I don't see you there, I'll see you in lecture Tuesday. Have a good one, everyone.